you take acceleration negative because it's acting opposite to the positive direction that you have. And if the positive direction is downwards, gravity is also acting downwards. In that case, you take it as positive. Okay, that's for gravity only. If you have some other forces, you have to think of those forces separately. Now, again, yeah, so you're saying it makes sense. Okay, that's good. Okay, so a railway engine of mass 120,000 kg is towing a coach of mass 60,000 kg up a straight track inclined at an angle of alpha to the horizontal where sine alpha is 0.02. So the angle is not that big. Let me actually make it slightly less steep like this. Let's say you have this inclined plane. This angle is alpha. We have a railway engine and a coach. Now, the engine is towing the coach up the plane. So we can say the engine is here. Let's call this R, the railway engine. And we have coach here. We know their weights and masses, right? And we know sine alpha. There's a light rigid coupling parallel to the track connecting the engine and coach. Okay, so there's a rigid object that is connecting these two things. Now that's important. When you have a rigid object, generally string can only pull objects. A rigid object can also push objects. So sometimes you need to remember this. If you do it the regular way that you deal with tension in general, sometimes what ends up happening in such cases is tension can come out to be negative sometimes. Okay, and that's okay. You just need to know that tension value can also be negative sometimes, because in that case, it would actually be acting opposite to the direction that you have assumed. Okay, so keep that in mind when you have a rigid object that's connecting two things. It could be a rod, it could be a tow chain, a tow bar. The tension value with your working could turn out to be negative, and that's okay. You don't have to get worried about that. And I explained that if it happens in this case, I'll also explain why that happens. Let's see if it happens or not in this case. So we have this track. And now it says the driving force produced by the engine is 125,000 Newton. So there's a driving force acting on the railway engine in this direction. That's 125,000 Newton. And there are constant resistances to motion of 22,000 to the engine and 13,000 on the coach. So there's a resistance acting on the railway engine, that's 22,000 Newton. And also a resistance acting on the coach that has a magnitude of 13,000 Newton. Find the acceleration of the engine and find the tension in the coupling. Okay, now let's represent all the forces. This looks like a standard Newton's second law of motion question. You have to find tension and acceleration. Now for this, you first have to represent all the forces acting on these objects. Now let's make it slightly bigger so that we have all the forces visible here clearly. Now these are the forces that they have explicitly told are acting. Right, this resistance here, for instance, is 22,000 Newton. And the driving force is also given. These are all the forces that are given. Now, what other forces that are acting that you have to think about yourself? There are four forces that you always have to consider if they're acting in a particular case or not. Weight, normal reaction, friction, tension. Okay, let's think about each of them one by one. So what about weight? Do we have weight? Yes, of course, any object has weight. What's the weight of the coach? It says the mass of the coach is 60,000 kilograms. What about weight? 10 times that. That's going to be 600,000. That acts vertically downwards. The engine has a weight. What's that? That's going to be 1.2 million in this case. So 1200,000. Okay, this times 10. Okay, what else? There's going to be reaction. Reaction acts perpendicular to the surface. So on coach, it acts in this direction. On the engine, it acts in this direction. This is the reaction. Let's call this engine, so we don't confuse the two R's. Okay, so we have reactions for both of them as well. What else? Is there friction? Well, there could be. We don't know whether the surface is smooth or not. However, they've already told us the resistances. So if there's any friction, it's already incorporated in resistance. We don't have to consider that separately. Okay, and since there's no friction that we have to account for, we can actually ignore reaction as well, because that's not going to be used in any case, right? Reaction is only going to be used in case there was friction, right? Okay, what else? Do we have any other force? Tension. On the coach, where does the tension act? On the coach, if you consider from the perspective of the coach, we say the tension acts in this direction, away from the coach. That's the standard direction that we take, okay? What about the engine? On the engine, we would say the tension acts away from the engine, right? That's going to be down the plane. That acts in this direction. And that's it. These are all the forces that are acting. Now, what we need to do first is we need to resolve the forces to see what forces are acting parallel to the plane, because that's the direction of motion. Parallel to the plane, we can apply Newton's second law of motion. Let's resolve the forces. So we have 600,000 Newton as the weight. What are going to be the components of 600,000? There's going to be one component. So remember, this angle is alpha. Then this angle here is also alpha. Component that is adjacent to alpha, that's going to have cos. So this component is 600,000 cos alpha, although we might not need that because that's acting perpendicular to the surface. And the other component in this direction, that is 600,000 into sine of alpha. That's this component. Okay, these are the two components of the weight of the coach. What about the weight of the engine? That also has two components. One component acts in this direction. Remember, if this angle is alpha, this angle here is also alpha. So this component is 120,000 cos alpha, in fact, 1200,000 cos alpha. And the other component that acts parallel to the plane, where do we represent that? Let's represent it here. This component is 1200,000 sine alpha. These are all the forces that we have acting on the coach and on the engine. All right. Now, let's be very careful. There are a lot of forces and you don't want to end up missing any force. So let's highlight the forces that we have for each of the objects. Let's talk about engine first of all. Remember, they're both moving up the plane, right? They're both moving up the plane. So the movement is up the plane. What are the forward forces and the backward forces for the engine first of all? There's a driving force here. There's a backward force tension here. There's a backward force resistance here. There's a backward force that's a component of weight here. These are the forces acting on the engine, right? There is nothing else there. What about the forces acting on the coach? There is tension acting in the forward direction. There is resistance. There is component of weight. And is there any other force? No. These are the forces. The blue ones are the forces acting on the coach. Okay. Now what we do is we apply Newton's second law of motion on both of them separately. So we have a coach and we have the engine. Let's start with the coach first of all. What are the forward forces? So what are we doing? We're applying Newton's second law of motion. Resultant force equals mass into acceleration, or we can say forward force minus the backward force equals mass into acceleration. There's no driving force for the coach. So driving force for coach would actually be this tension. Okay. The coach is not driving itself. It's being towed by the engine, right? So only the engine has that driving force. But for coach, it's the tension that's making it move in the forward direction. So for the coach, tension would be the driving force. Okay. All right. So now, what are the forward forces for a coach? Tension. Backward forces 600,000 sine alpha. You have to be very careful with the number of zeros here. Okay, because that will be a common error in this question, I suppose. Minus 13,000. That equals mass of the coach. What's the mass of the coach? Mass of the coach is 60,000 into acceleration. That's one equation that you've got. Now they have given you the value of sine alpha. The value of sine alpha is 0.02. You can input that here directly. 600,000 into sine of alpha, which was 0.02. And this becomes minus 13,000 equals 60,000 into A. That's one equation that we are getting. Let's try to simplify this. 600,000 into 0.02. That's giving me 12,000. So T minus 12,000 and 13,000. That's 25,000. T minus 25,000 equals 60,000 times A. That's one equation that we've got. All right. Now you don't have to find the angle first and then find sine of that first. They've given the value of sine alpha directly. Just use that directly. Sine alpha is 0.02. Okay, just put that directly here. That's one equation that we have. You can do the same thing for the engine as well now. What are the forces acting on the engine? What are the forward forces? Forward force is this driving force. That's 125,000. Yeah, 125,000. That's the forward force. What are the backward forces? Tension, this 22,000 resistance, and the component of weight. Okay, these are the backward forces. So we have 125,000 minus T minus 22,000 minus 1200,000 into sine of alpha. That equals mass of the engine into acceleration. What's the mass of the engine? It's 120,000 into acceleration. That's the second equation that we're getting. Now, again, we do the same thing here as well. 125,000 minus T minus 22,000 minus 1200,000 into 0.02 equals 120,000 into A. There will be a lot of careless errors in this question if you're not very careful, because there's so many zeros. You can end up missing one or adding one extra. So be careful about that. Okay, so what are we getting from this? 125,000 minus 22,000 minus 1200,000 into 0.02. And that's giving me 79,000 minus T equal to 120,000 times A. This is the second equation that we're getting. Just solve these two simultaneously now, and you would get the value of T and A from this. From the first equation, we get T equals 25,000 plus 60,000 times A. And from the second equation, we have T equal to 79,000 minus 120,000 times A. Now we can just equate both of them. All right, just equate both of them and see what that gives you. 25,000 plus 60,000 times A, that equals 79,000 minus 120,000 times acceleration. You can see what the value of A turns out to be from this. 60,000 plus 120,000. $79,000 minus 25,000 whole divided by the answer. I'm getting A equal to 0.3, right? Is that okay? Acceleration is this. And now what about the tension? The tension turns out to be 25,000. You put that back in any one of those two equations. 25,000 plus 60,000 into 0.3. You can see what that turns out to be. This is 25,000 plus 60,000 into 0.3. And that's giving us 43,000. That is the value of tension that we're getting. Tension is 43,000 Newton. Okay, and that's what we wanted. Yes, you can do that as well, Harsha. You can use the whole system, but that will only give you acceleration. For tension, you would still have to use either this or this. Okay, you have to make one of these equations anyway. If you use whole system, there is actually a chance of, there's a higher chance of making plus minus errors. So I generally do not prefer using equations for the whole system. If you're very comfortable with that and are sure that you would not make plus minus errors in that, that's perfectly okay. You can do that. But otherwise, I generally prefer making separate equations for both of them. Okay. All right. So that was 5 marks, and that's what you had to do here. This is the Newton's second law of motion. It's actually F equals ma, but just to point out that the force is resultant force, I use result RF there. That's resultant force. You might have seen it as forward force minus backward force equals mass into acceleration. It's that formula basically. Why do we use this? Because we have some forces, we have acceleration, we have a force missing, we have acceleration missing. What equation connects those two things? Resultant force equals mass into acceleration. That's Newton's second law of motion. Okay, that's why we're using this. So in general, whenever you have a problem that asks for acceleration and tension at the same time, acceleration and tension is a force, and you have acceleration, what connects these two things? F equals ma. So that's always what you have to do in problems like these. Why two tensions? Well, because that what are they calling that rigid coupling, that's basically connected to both of the objects, both the engine and the coach. So both of them will have a force. So it would be applying a force in both of them. And in which direction does that force apply? On the coach, it applies in the forward direction. On the engine, it applies in the backward direction. Since the engine is connected to the coach is basically pulling the engine backwards as well. So that's why we have this tension as well, acting in the backward direction. So it acts in both directions, right? So it depends on which perspective you're talking about. If you're talking from the perspective of the coach, on the coach it applies in the forward direction, up the plane. If you talk from the perspective of the engine, on the engine the tension acts down the plane. So it depends on what object you're talking about, from which perspective you're talking about. Okay, so tension acts on both the things. Whichever object the rigid coupling is attached to, is connected to, it applies a tension on that. Okay. All right, now it says at an instant when the engine is traveling at 30 meters per second, it comes to a section of track inclined upwards at an angle beta to the horizontal. The power produced by the engine is now 4,500,000 watt, and as a result, the engine maintains a constant speed. Assuming that the resistance forces remain unchanged, find the value of beta. Okay, so what's happening now? We have another track now. It's a section of a track that's inclined at an angle beta to the horizontal now. So now the angle is beta. Okay. This is the engine. It's traveling in this direction. We have already found the tension in the previous part, although that's not relevant anymore. I'm sorry. Okay, so what are the forces acting in this direction now? On the engine, we have some forward forces. There'll be a driving force. We don't know what that is right now because the driving force that was given for the previous part, that's not relevant anymore. Okay. What are the other forces acting? There is tension because of its connection with the coach. So it's the same figure as before, basically. So you have tension acting in this direction on the engine. Let me make it slightly bigger. What else? There is component of weight. Where does weight act? Weight acts vertically downwards, but we've already resolved the weight earlier. It was 1200,000 sine alpha. Now, since the angle is beta, we could say the component of weight acting here is 1200,000 sine of beta. That's the component of weight. What else? The question said, there are constant resistances to motion of 22,000 Newton and 13,000 Newton. So they are still acting, right? There's a resistance of 22,000 Newton and 13,000 Newton. Let's represent that as well. On the engine, it was 22,000. So there is another force acting down the plane. That's 22,000 Newton. So we have tension, 22,000 and this. These are all the forces acting on the engine in this case. What about the coach now? What are the forces acting on the coach? Let's think about that. On the coach, there is tension because it's connected to the string, to the coop length. It's connected to that. So there is this tension acting. What else? There is going to be resistance. What was the resistance for this? For the coach, resistance was 13,000 Newton. What else? There was the component of weight. Component of weight in this case was 600,000 sine alpha. In this case, the angle is beta. So we say 600,000 sine of beta. These are all the forces that are acting in this case. Okay. So again, we have represented the forces that are acting. Now, what additional information is given now? It says, at the instant when the engine is traveling at 30 meters per second, the power produced is now 500,000 watts. And because of this, the engine maintains a constant speed. What does that mean? If the speed is constant, what about acceleration? Can we say anything about that? Acceleration is going to be 0. Okay. So we can put acceleration equal to 0. And we have power given. How do we use power here? Well, power equals driving force into velocity. We have the power value. We have the velocity value. What we can do is we can find the driving force using this. Let's see what that turns out to be. 4,500,000 equals driving force into 30. And that will give you the value for the driving force. 4,500,000 divided by 30, that's 150,000. So the driving force, therefore, is 150,000 Newton. The power that's given, that helps you find the value of the driving force. So now that we have that as well, now we can again use the same thing as before, apply the Newton's second law of motion on both the objects. Let me see what information we have here. Do we need to find tension? No, we only need to find the angle beta. Now in this case, Hashir, it might be a better idea to use the whole system because you do not need to find the value of tension. If you needed to find the value of tension, in that case, it would have been better to just make two separate equations. But in this case, you see, they are not really asking us for the value of the tension. So what we can also do in this case is we can consider the whole system. What's the whole system? C and E together, and look at the forces that are acting on both of them at the same time. Tensions are going to get cancelled out because one is acting in this direction, one is acting in this direction. And we can just consider the whole system together. If you still want to do them separately, you can do that. You'll have to make T the subject in both of them and then equate them. That's also possible. Or you could use the whole system. If you use the whole system, you would get something like this. Driving force minus 22,000. That's this one. Minus 1,200,000 into sine of beta. Minus 600,000 into sine of beta. Minus 13,000. That equals mass, the total mass, whatever that total mass is, it doesn't matter because the acceleration is 0, it's going to become 0. This could be an equation that you get. Now you know the driving force, you can find the value of sine beta from this. This could be one idea, you could do that. However, if you do not know how to use the whole system, I think most people do it separately. Let me just show you that way as well. If you were to use both of them separately, this is how it would work. You would apply Newton's second law of motion on both the objects separately, one by one. On the coach, it's going to look like this. T minus 600,000 into sine of beta minus 13,000. Was there any other force? Are we missing something? No. That equals m into 0. Whatever the mass is, since the acceleration is 0, the right side becomes 0. And that is going to give us T equal to 600,000 into sine of beta plus 13,000. That's one equation that we get. If we talk about engine, we have a driving force. Driving force now has this value. We found that out, 150,000. So 150,000 minus 22,000, that's the resistance, minus the component of weight, which is 1,200,000 into sine of beta. That equals mass, whatever the mass is, into 0, it becomes 0. You also had tension, we missed tension here, minus T as well. There's also tension acting in the backward direction. Now you make T subject here as well, and that will give you T equal to 150,000 minus 22,000, that's 128,000, minus 1,200,000 into sine of beta. Now you equate these two equations because you have T the subject in both of them, and that will give you the value of beta. Let's see what that turns out to be. 600,000. Again, be very careful about the number of zeros. Plus 13,000 equals 128,000 minus 1,200,000 into sine of beta. That's what we get. Now take sine beta terms to one side, make that the subject and see what that gives you. 128,000 minus 13,000. This needs to be divided by 60,000. Plus 1,200. Is that 600 or 60? 600,000 plus 1,200,000. I'm getting sine beta equal to 0.063,889, something like this. And then you take sine inverse of that and see what that gives you. Look at my calculators in radian mode. Let me just change that to degrees. In mechanics, you should always use degrees. 0.063,889 sine inverse of that. That's giving me 3.66 degrees. That's the angle that we're getting. Okay. 3.66 degrees. If you wanted to round it off to 1 decimal place, that will be 3.7 degrees. Okay. Now this question is not that difficult. The reason it has become so long is because of these values, as in so many zeros. Because of that, it has become more complicated than it actually is. But you will see other questions like this in the past papers as well, exactly the same idea. So if you've practiced enough, you should have been able to figure this out, because you'll find at least 4 or 5 other questions very similar to this, almost exactly the same in the past papers. So that's what you would do. Okay, that was part B of this. Let's do 6 and 7 first, and then we can possibly come back to question number 4 as well. Okay, it is an elevator is pulled vertically upwards by a cable. The elevator accelerates at 0.4 meters per second square for 5 seconds, then travels at a constant speed for 25 seconds. The elevator then decelerates at 0.2 meters per second square until it comes to rest. Find the greatest speed of the elevator and hence draw velocity time graph for the motion of the elevator. Okay. It accelerates at 0.4 meters per second for 5 seconds. Do we know at what point it starts? Point 0.4 meter per second square for 5 seconds. We can actually find the initial speed using that. Okay. So what's the first part of the journey? Let's consider the first part of the journey. In the first part of the journey, what information do we have? We're talking about this part. In the first part of the journey, we are given that the acceleration is 0.4 and it's moving upwards, right? And the time taken for this part is 5 seconds. In the second part of the journey, it travels at constant speed for 25 seconds. That's the second part of the journey. So in this case, we can say acceleration is 0 and velocity, initial velocity, final velocity, all of them are just going to be 25. So we can say U is 25 and V is 25, or we can just write that V equals 25 and that's a constant value. So we can say U equals 25. If you want to use constant acceleration formulas here as well, V is also 25 because, no, sorry about that. I read that wrong. It's time, it's not speed. Time is 25 for in the second part of the journey. Okay, so 25 seconds means it's time from 5 seconds to 30 seconds. The first part of the journey was from time 0 to 5. And the second part of the journey then is from time 5 to 30. And then what happens is it decelerates at 0.2 meters per second square until it comes to rest. So in the final part of the journey, the deceleration is 0.2. So that means acceleration is minus 0.2. Now, what's the time duration for that? We don't know that. It just says that it's 0.2 meters per second square. That's all that we're given. Okay. Until it comes to rest, we also know the final speed, by the way, V equals 0. Now, what's the time duration for this? We do not know that for this part, right? That's all the information that we're given. Now, since it's pulled vertically by a cable, I think we can actually just understand from that that it starts from rest, then it starts getting pulled by the elevator. So we can basically assume the starting speed to be, initial speed to be 0, right? Because when the elevator starts, even though it does not explicitly mention that here, but it's supposed to start from rest, right? When it starts getting pulled by a cable. So initial velocity is 0. If the initial velocity is 0, can we find the final velocity after 5 seconds? Can we figure that out? We've got U, A, and T. Which equation can we use for that? For the first part of the journey, we can use V equals U plus AT, and that will give us V equals 0 plus 0.4 into 5. What does that give us? V turns out to be 2 meters per second. That's the first part of the journey. Now, since it reaches a speed of 2 meters per second after the first 5 seconds, and then it becomes constant, at what speed is it supposed to get constant? Whatever speed it reaches after 5 seconds. So at this speed, it becomes constant then. Okay. So it becomes constant at this point. So we can say in the second part of the journey, therefore, its speed is supposed to be 5 meters per second. And since the speed is constant in this part, initial speed is 5, and also the final speed is going to be 5 as well. That's the second part of the journey. Now, if that is the speed in the second part of the journey, and the speed remains constant, I'm sorry, it's going to be 2, not 5. So yeah, we had 2 here. So this should be 2 and 2. I mixed up with the time value here. So initial velocity is 2 and the final velocity is 2. All right. Now it's moving at constant velocity for the second part of the journey. At the 30-second mark, it is still moving at 2 meters per second. So what happens in the third part of the journey now, which starts from time 30? What is going to be the initial speed in this part of the journey? Initial speed is going to be 2 meters per second. And now using this information, what we can do is you can find the time taken for the last part of the journey. What does that look like? In the third part of the journey, can you find the time taken? You've got u, v, and a. Which equation connects these 4 things again? V equals u plus at. And now you can say in the last part of the journey, v is 0, u is 2, a is minus 0.2, and then you can find t from this. What does that turn out to be? 2 over 0.2, that is 10 seconds. So for the last part of the journey, the time duration is 10 seconds. If the time duration is 10 seconds, it starts at 30 and ends at 40. Now that is all that we need to be able to sketch or draw a velocity time graph for the motion of the elevator. In fact, they also asked us to find the greatest speed. What's the greatest speed? We have found that value here already. The speed at which it becomes constant after 5 seconds. This is the greatest speed that we were looking for. And now we need to draw or sketch the velocity time graph for this. How would we do that? It starts from time 0. This is velocity, this is time. It starts at 0 and ends at 40. In the middle, you would have 20 somewhere. What are the important points? Let's say this is the 5-second mark. That's an important point. This is the 30-second mark. This is an important point. These are the important points at which you've got to mark the velocity value. What's the velocity initially? It starts from rest. So it starts from 0 here. At 5-second mark, its velocity becomes 2 meters per second. We have found that here. And that's the greatest velocity. We can mark that here. At 5-second mark, the velocity becomes 2 meters per second. And then it travels for constant velocity until 30 seconds. So we can mark another point here. Then it comes to rest again. Now in the initial part, its acceleration is constant. And in the final part as well, its deceleration is constant. So what is the graph going to look like? It's going to be straight lines like this because it's a velocity time graph. The gradient of velocity time graph represents acceleration. Since acceleration is constant in the first part and the last part, we're just going to have straight lines like this. We have a straight line here. We have a straight line in the first part like this. We have another straight line in the last part like this. In the middle, since the velocity is constant, we just have a horizontal line like this. Okay. This is what the velocity time graph for the motion of this object looks like. Okay, just straight lines like this. Now it says find the total distance traveled by the elevator. It's a velocity time graph. Well, I just explained that. What exactly do you not understand here, Mustafa? That was pretty straightforward. We just marked the velocity points. And then since acceleration is constant in the first part, it's constant in the last part, it's got to be straight lines, right? We just mark the points and join them by straight lines because acceleration is constant. Gradient of a velocity time graph represents acceleration. Since acceleration is constant, the gradient is constant. Okay? And that's why we've got straight lines, because straight lines have constant gradients. Now it says find the total distance traveled by the elevator. It's a velocity time graph. The area under the velocity time graph gives you displacement. In this case, displacement and distance are going to be the same because there's no change in direction. So we can just find the area under the graph. What is that going to be? It's a trapezium. What are the sides of this trapezium? This is 40. And the upper side is 25. What's the sum of parallel sides? It's 40 plus 25 multiplied by height. Height is 2. So the area under the graph turns out to be 65, and that's the distance traveled by the elevator as well. Okay, just find the area under the graph for the velocity time graph. Okay, now part C says the mass of the elevator is 1200 kilograms, and there's a crate of mass m/kg resting on the floor of the elevator. Given that the tension in the cable on the elevator is decelerating, is 12,250 Newton. Find the value of m. Okay, now that's interesting. This is a standard method again that you need to know about, how to deal with objects in an elevator moving up and down. Okay, you need to understand this concept well. Now, let's think about this. So we've got an elevator. Let's say this is what it looks like. The mass of the elevator is 1200 kg, and there's a mass inside the elevator of m kg. Let's represent that here. This is m kg inside the elevator. Given that the tension in the cable when the elevator is decelerating is 12,250 Newton. Tension in the cable. Now remember, where is the elevator being pulled? It's going upwards. It's being pulled upwards by a cable. So the cable is applying a force in this direction, right? This is the tension. And they're saying the tension has this value. It's 12,250 Newton. That's the value of tension. Okay. That's one force that's acting on the elevator. What was the deceleration in this part? Deceleration in this part, do we know that? Deceleration, yeah, that's 0.2. So deceleration is 0.2. What does that tell us about the acceleration? Acceleration value is going to be minus 0.2. Okay, acceleration is minus 0.2 in this last part. Okay, now what we can do is we've got acceleration, we've got forces. How do we connect forces and acceleration? What's the formula that connects forces and acceleration? It's the Newton's second law of motion, F equals ma, or the resultant force equals mass into acceleration. Let's think about all the forces acting on this elevator and the mass inside the elevator. Let's talk about the elevator first of all. There's an upward force of 12,250 Newton acting on the elevator. That's the tension in the elevator. What about the downward force on the elevator? So of the whole system, think of the whole system first of all, because the tension is acting on the whole system. On the whole system, what is the overall force acting in the downward direction? You've got this mass and you've got the mass of the elevator. The total weight acting downwards, what's that? That's 1200 plus m multiplied by 10. What does that become? That becomes 12,000 plus 10 times m. This is the total weight acting in the downward direction. Okay. What you can do now is you can say, if you think of this whole elevator, resultant force equals mass into acceleration. What's the forward force? In which direction is the elevator moving? It's moving in the upwards direction. What's the forward force? The forward force is 12,150. What's the backward force? The total backward force, the total downward force in this case, that is the weight of the elevator and the weight of the mass inside the elevator together. This equals mass of what? Mass of this whole thing. What's that going to be? 1200 plus m, right? The total mass of the elevator and that object into acceleration. Acceleration value is minus 0.2. You can solve this equation and that should give you the value for m. Let's simplify this. What do we get from this? 12,250 minus 12,000 minus 10 times m, that equals minus 0.2 into 1200, that's 240, minus 240 minus 0.2 times m. Now 10 comes to the right side and that's going to give you 10 minus 0.2, that's 9.8 times m. And the other side you have 12,250 minus 12,000 plus 240, and that's 490. And the value of m from this turns out to be 490 divided by 9.8. The mass inside the elevator is 50 kilograms. And that's what we were looking for. That's the mass inside the elevator. So we look at the whole system and we see the tension acting upwards was this, the total force acting downwards was this. Apply Newton's second law of motion on that, and you get the mass for that. All right. If you had to apply Newton's second law of motion on the object inside the elevator, how would that work? On this object, so it's not required here, but if they asked you for the reaction acting on the block inside, how would you calculate that? Think of this mass. What are the forces acting on this mass inside the elevator? So on that box inside the elevator, what are the forces acting? That box is also moving upwards along with the elevator. So if you think of the box individually, box separately, what are the forces acting on the block? In the upwards direction, there is reaction from the elevator, okay? For the mass inside, reaction acts as the forward force because of that, the block is moving upwards. So if you were to write down an equation for the block inside the elevator, that will look like this: R minus weight of the block, which is 10 times m, that equals mass into acceleration, which is minus 0.2. So you could find the value of normal reaction like this as well. Sometimes they ask you to find this as well. Along with the value of m, they could also ask you to find the value of r here. And this is how you would do that. Okay. But in this case, we could just use this whole system to find the value of m. All right. Now it says, find the greatest magnitude of the force exerted on the crate by the floor of the elevator and state its direction. Well, they actually asked about this in the very next part now. Greatest magnitude of the force exerted on the accelerator by the floor of the elevator. Okay, so again, let me just copy that figure here. this is what the situation looks like. Okay. But now the tension is not 12,250 anymore, because when it's decelerating, that means the floor of the elevator is applying less force on that, right? Because it's decelerating at less speed. So that tension is no longer relevant. That was written inside part C. That was the case when the elevator was decelerating. But now that we know the value of M, the value of M is not going to change. The mass remains the same, right? That was 50 kilograms. That is still 50 kilograms. So now the total mass of the elevator and the object inside, that's 1200 kilograms and 50 kilograms. So what's the total force acting in the downward direction in this case? The total force acting on the whole system in the downward direction is 1250 kilograms. There's going to be some tension acting in the upwards direction. Mass of the block inside we know is n kilograms, which now is 50 kilograms. What they're asking for is find the greatest magnitude of the force exerted by the floor of the elevator. What's the force exerted by the floor on the crate of mass? It's this reaction, right? That's the force that the floor of the elevator is applying on that mass. They ask us for the greatest magnitude. When is the force exerted by the floor on the mass is going to be great? When is that going to be greatest? That force is going to be the greatest when the elevator and the block, they are accelerating. When they're accelerating, right? When were they accelerating? They were accelerating at 0.4 meters per second square. That is where the force is going to be the greatest, when they're accelerating. Because in order to make the object accelerate, it would be applying a greater force on the block. So we consider that part of journey when the acceleration is 0.4. Now let's think about this. When acceleration is 0.4, can we find any of these unknowns here? Since we are looking for the value for reaction, let's apply Newton's second law of motion on the block inside and see if that can give us the result directly, and we might not need to use the whole system there at all. Yeah, we don't need to do that because we only have one unknown if we look at the crate of mass. So now we are focusing on the crate of mass. Look at the forces acting on the crate of mass. Let me represent that outside. There's reaction acting upwards and there's weight acting downwards. What's the weight acting downwards? 50 kg is the weight, is the mass. Weight is going to be 500 Newton. And these are the only forces that are acting. We need to find the value of the greatest force would be when acceleration value is 0.4. You just apply Newton's second law of motion here. That's resultant force equals mass into acceleration. The forward force is reaction here. Backward force is the weight of the object. That equals mass. Mass is 50 kilograms into acceleration. That is 0.4. And that should give you the value for R here. Let's see what this turns out to be. 500 plus 50 into 0.4. And that's giving me, 500 into 50, plus 50 into 0.4. That's giving me 520 Newton. That's the magnitude of the force exerted on the block by the floor of the elevator. And they also ask you for direction, stated direction, in which direction does this force act. Reaction is acting up the plane. So we say, in the upwards direction, we say it's 520 Newton in the upwards direction. That will be the reaction in this case. That's the force exerted on the block by the surface. If they asked you for tension here as well, for that you could consider the whole system. You could say T minus 1250. That would equal mass, the total mass, I'm sorry, t minus 12,500, because this is mass, weight would be 12,500, equals mass, which is 1250 into acceleration, which is 0.4. And you can find the tension using this equation in that case as well. All right, but that's not what you're looking for. If you were looking for that, you could find that using the whole system like this. In this case, we were looking for reaction. For that, we used an equation for the mass inside the elevator. Is that okay? Any problems with this? No problems? Yeah. Okay, good. Let's look at the next question now. Question number 7. Now we've got the diagram that shows the vertical cross section. Okay, I'm sorry. Why do I get these messages late? Why is it the opposite? Like, why is it not 12,000 plus 10M? Well, Josefa, it's about the direction of motion. In which direction is the elevator moving? Elevator is moving in the upwards direction, right? So whichever direction the elevator is moving in, that's the positive direction. Okay. It's moving upwards. So the direction in which it's moving, you take that as the forward force, and the opposite force is taken as the backward force. Okay. That's why we are doing 12,250 minus this. And make sure on the right side, for acceleration, you've got negative 0.2, right? Because it's deceleration, the acceleration value will be minus 0.2. Okay, good. Because this sometimes comes along with momentum. Sometimes it comes with Newton's law of motion. In this case, it's also coming with energy, and that becomes more complicated. These equation questions are mostly relatively straightforward. And in this case as well, it was not that difficult. Okay, let's have a look at this one last question now. Question number 7 from this paper. It says 2 particles A and B of masses 3m kilograms and 2m kilograms respectively. They are attached to the ends of a light and extensible string. The string passes over a fixed smooth pulley which is attached to the edge of a plane. We must hide the important information. This is 3m, this is 2m. The plane is inclined at an angle theta. A lies on the plane and B hangs vertically, 0.8 meters above the floor, which is horizontal. Initially, A and B are at rest. Given that the plane is smooth, find the value of theta for which A remains at rest. Okay. The value of theta for which A remains at rest. If A remains at rest, that means we are looking for the value where the opposite forces here remain equal to each other, right? What are the forces acting on B? At B, we've got weight of B. What's that? If 2m is mass, weight is going to be 2m into 10. That's 20m. And there's tension acting upwards. What are the forces acting on A? We've got weight of A. That's 30 times m. We've got reaction. Although in this case, we would not really need to use that because the plane is smooth. So reaction is not going to be used. We only use that generally when there's friction. But then you have components of, so there's also tension, by the way. You have components of weight. If this angle is theta, this is also theta. This component of weight is going to be 30m into cos of theta. And the other one is going to be 30m sine of theta. Now we just equate opposite forces. T equals 20m. And from here, T equals 30m sine theta. So T equals both of those things. We can get an equation directly. We can say 30m sine theta should equal 20m. Right? If we consider the whole system, we can say this value should equal this value. All right. You can do that individually as well. You will say t equals 30m sine theta. And then from here, t equals 20m. You just equate both of them and you get this result. Okay. Now m and m get cancelled and sine theta equals 2 over 3. 20 over 30, that's 2 over 3. You can see what the value of theta here turns out to be. Sine inverse of 2 over 3. Let's figure this out. That's 41.81 degrees. 41.8 degrees, that's the first part. Okay, so we just resolved the forces, equated the opposite forces. Now it says it's given instead that the plane is rough. Theta equals 30 degrees and the acceleration of A up the plane is 0.1 meters per second square. Show that the coefficient of friction between A and the plane is under root 3 over 10. We need to find the coefficient of friction. And now we're given that the plane is rough. Angle is 30 degrees. So theta is 30 degrees. And acceleration is also given. That's 0.1 meters per second square. Now that the plane is rough, acceleration of A up the plane. So A is moving up the plane. They've given that information here. If A is moving up the plane, what about friction? Friction is going to act down the plane. It's going to oppose the motion. That's where friction acts. And now we need to find the coefficient of friction. What do we do in this case? Let's consider both the particles one by one. We've got particle A and the particle B. Now for A, forces acting perpendicular to the surface, they are always equal. R equals 30m cos theta. These two are going to be equal, right? R and 30m cos theta. R equals 30m cos theta. And in fact, angle is 30 now. Let's put that here, cos 30. What does that give us? 30 into cos 30. Let's do that on the calculator directly. 30 cos 30, that's giving me 15 under root 3. 15 under root 3 times m, that's the value of R. Okay? Perpendicular to the surface, these forces are always equal to each other. Now what happens along the surface? What's the forward force? A is moving up the plane. The forward force is tension. Backward forces are friction and 30m sine theta. So we say, in this case, we apply Newton's second law of motion. Resultant force equals mass into acceleration. Because along the surface, there's movement. P minus friction minus 30m sine theta. Right? These are the forces acting opposite to motion. That equals mass, which is m, into acceleration, which is 0.1. Okay. And now we can say P minus F, since the object is moving now, friction is at its maximum value, mu into R, minus 30m into sine 30. Let's actually input that here. Sine of 30 degrees. Sine 30 is 1 over 2, so that becomes 15 times m equals 0.1 times m. Now T minus mu into R value is this. We can say T minus mu into 15 under root 3 times m minus 15m. Or let's actually take it to the other side. 15m goes to the other side. It becomes 15 plus 0.1. That's 15.1 times m. That is one equation that we're getting in terms of T and M. T, mu, and M. Okay. Let's talk about B now. B is moving down the plane, right? B is moving down the plane. For B, the forward force is 20m. Let's use resultant force equals mass into acceleration on that as well. Forward force is 20m, backward force is tension. Right? B is moving down the plane, 20m is the forward force. B is moving downwards, not down the plane, it's moving downwards. 20m is forward, T is backwards. That equals mass of B, which is 2m. Okay, I'm sorry about that. mass was not m. For A, the mass was 3m, and for B, the mass is 2m. Let me correct that here. On the right side here, it should have been 3 times m. So it's 3m into this. That becomes 0.3m and 15.3m. For B, the mass is 2m. Okay, so it becomes 2m into acceleration. Okay, I'm just checking if I have used 3m anywhere else on the left side. 2tm, this is fine. It was coming from there. Okay, let's look. Now we know the value of acceleration as well. What's acceleration? Acceleration is 0.1. Let's input that here as well, and that gives us 20m. Or let's make t the subject. 20 minus 0.2, that's 19.8. 19.8 times m. That's the value of tension that we get from the equation for B. Now put that in the first equation. What does that give you? 19.8 m minus 15 under root 3m times mu. That equals 15.3 times m. Now m is appearing in every single term. All terms have m. We can take that common, remove that, and that leaves us with 19.8 minus 15 under root 3 times mu equal to 15.3. Now we need to make mu the subject. It's going to be 19.8 minus 15.3 divided by 15 under root 3. Put that on your calculator. Hopefully it should give you something like this. Try that. 19.8 minus 15.3. That's 9 over 2. So you can write it like this if you want first. 9 over 2 over 15 under root 3 divided by 15 under root 3, and that simplifies to under root 3 over 10. And that's what you have to prove. 1 over 10 under root 3. Put that on your calculator. Your calculator will do this work for you. You get this from that. 1 over 10 into under root 3. This is what we had to prove there. All right, that's the value of mu that we were looking for. We have proved that. That's part B. Make sense? Now let's look at the next one. It says when B reaches the floor, it comes to rest. Okay, now what's happening is B is going downwards, and at some point it hits the floor, and when it hits the floor, it comes to rest. Find the length of time after B reaches the floor for which A is moving up the plane. You may assume that A does not reach the plane. Okay, now again, it's that type of problem where the string becomes slack at some point. There's a lot of clutter on this diagram already. You will do this using a pencil, as in annotating on the diagram. That will be done with a pencil, so that for the next part you can erase that. I can just copy this like this. Okay, so this is what the diagram looks like. It says when B reaches the floor, it comes to rest. Okay, now B is moving downward, and A is moving up the plane. At some point, B hits the ground. A would have traveled the same distance in this direction. How much is that distance? 0.8 meters. The distance that B is above the floor initially. Okay. Let's call this point something. Remember, in such problems, we break the journey into multiple parts. We say, let's say this point is X, let's say this point is Y. And now at Y, A would have some speed, right? It would not be 0 at this point. It would be some positive speed. Let's say that's 2 meters per second. Let's assume, I'll change that, but it will be some speed, right? It's not going to come to instantaneous rest here. It will move on for a while, and then gradually its speed is going to become 0. All right. So now we can say after Y, it moves on for a while until its speed becomes 0 at this point. Let's call this point Z. Now remember, we were given this at the start of part B. It's given instead that the plane is rough. It's before part B. That means this condition also applies to the third part. Okay, part C also has a rough plane. Okay. Now, what does that mean? Let's break this journey down to 2 parts, from X to Y and Y to Z. Now, from X to Y, let's see what information you've got. A is moving up the plane. What do we know about the particle from X to Y? Its initial velocity, it started at the point X, it started from rest, did it? Yeah, so it started from rest. From X to Y, initial velocity is 0. We're talking about particle A, right? Initial velocity is 0. What else? We know acceleration. From the previous part, we found the acceleration while the string was taut. So remember, from X to Y, the string was taut. At Y, B hits the ground, and when B hits the ground, the string no longer remains straight, so it's no longer taut. From Y to Z, we would say that the string is slack. We're talking about X to Y part for now. From X to Y part, do we know acceleration? Have you found that in the previous part? In fact, they've given this acceleration. They're saying acceleration is 0.1. So for this part of the journey, we also know acceleration, that's 0.1. Do we know displacement? Yes, we also know displacement. Displacement from X to Y is 0.8. And now what we can do is, remember what we do in such problems, Y is the common point between these two parts of the journey. So at Y, we can find the velocity because that will serve as the initial velocity for the next part of the journey. Let's find final velocity for this. V, A, S, and U, which equation connects these 4 things? 2AS equals V squared minus U squared. What do we get from that? 2 into 0.1 equals V squared minus 0 squared. We will get a value of V from this. That's square root of 0.2. That's the velocity of the particle at the point Y. Now that becomes initial velocity for Y to Z part of the journey. So here, initial velocity is under root 0.2. Now, what about the final velocity? When it reaches its maximum point, its velocity is going to be 0. So we also know the final velocity. What we need to find is the time taken after B hits the floor. So basically time taken from Y to Z. T is what we have to find out. Do we have any other information? We don't know what the distance from Y to Z is. We don't know what the... Okay, I'm sorry about that. Yeah, thank you. This is 2 into 0.1 into 0.8. There was 0.8 there as well, which I missed. That becomes 0.2 into 0.8, which is 0.16, 0.16, and the square root of that gives me 0.4. This velocity is actually turning out to be 0.4, not 0.2. Let me check that again. 2 into 0.1 into 0.8, and then square root of that, that's 0.4. Okay. Initial velocity is actually 0.4, not under root 0.02 as I wrote earlier. Okay, so now we have initial velocity and the final velocity. We don't have time. That's what you have to find out. We don't have displacement. We don't have acceleration. Can we find any of those things? Displacement is not given. Can we find acceleration somehow? We can find acceleration using forces now. From y to z. Let's think about the forces acting on the particle in this part of the journey, from y to z. Let's say the particle was here. What forces are acting? There's no forward force because there was tension earlier, but now there's no tension. There's only weight component that's acting against motion. We calculated that earlier. That was 30m into sine theta and friction. These two forces are still acting. 30m sine theta and friction. I'm actually represented on the side here. From y to z, we know there's friction acting in this direction. There is 30m sine theta acting in this direction. So what about acceleration? We can use resultant force equals mass into acceleration to find the acceleration for this part of the journey. What would that be? Is there any forward force? There's no forward force. Backward force is friction and 30m into sine of 30. Angle is still 30 here. Yeah. That equals mass of particle A, that is 3m, into acceleration. You can find acceleration of the particle using this. Now we already know that friction is equal to mu r, and we have calculated that earlier. Mu r is the same as before, right? 15 under root 3. Mu r becomes this. 15 under root 3 into m into mu. 15 under root 3m times mu minus 30 sine 30 is 15 times m, that equals 3m times a. A is appearing in every single term, that gets cancelled, and we're left with minus 15 under root 3 times mu. Minus 15 equals 3 times acceleration. In fact, we already know the value of mu. We found that in the previous part. Mu is under root 3 over 10. We can also input that here. Let's input the value of mu here as well. That was under root 3 over 10. And that is going to give you the value for acceleration. Minus 15 into 3 divided by 10, minus 15 divided by 3. Acceleration is turning out to be minus 6.5 for me. From y to z, this is the acceleration that I'm getting, minus 6.5. Now what we can do is we can say this is the acceleration for y to z part of the journey. Let's use that here. Acceleration is minus 6.5. And now what are we looking for? We're looking for time. Which equation connects these four things? V equals u plus at, and that is what is going to give us the value of time. 0 equals 0.4 minus 6.5 times t, and the value of t turns out to be 0.4 over 6.5, which is 0.06154, or you can say 0.0615. And that's the value of t that we get here. That's our final answer. That's the time taken to go from y to z here. Because for 7 as well, then there are not many votes. Although it looks kind of tricky. Have a look at question number 7 as well. Let me know if you can do that. Okay. On a straight horizontal test track, driverless vehicles are being tested. A car of mass 1,600 kilograms is towing a trailer of 700 kg along the track. The brakes are applied, resulting in a deceleration of 12 meters per second. The braking force acts on the car only. In addition to the braking force, there are constant resistance forces of 600 Newton on the car and 200 Newton on the trailer. Find the magnitude of the force in the tow bar. Okay, now how do we think about this? It's a horizontal test track, right? So the track is horizontal. It looks like this. Okay. Okay, this is a horizontal test track. It says driverless vehicles are being tested. The car of mass 1600 kg is towing a trailer of mass 700 kg. So there's a car that's towing a trailer. Let's say this is the car and this is the trailer. Since the car is towing the trailer, we can assume that the car is moving to the right side. There will be some driving force maybe, or in this case, in fact, brakes are applied, so there's no driving force. Masses are given for both of them. There's a deceleration of 12 meters per second square. The braking force acts on the car only. In addition to the braking force, there are constant resistance forces of 600 Newton on the car and 200 Newton on the trailer. Okay, so this is all the information that's given. Find the magnitude of the force in the tow bar. Magnitude of the force in the tow bar. Now, what's that? Let's look at all the forces that are acting on these two vehicles. Let's talk about the car first of all. Remember, they're connected by a tow bar. So let's represent that like this. On the car, first of all, is there any forward force? We are assuming that the car is moving to the right. There's no forward force at this point. There's no driving force at this point. Why? Because the brakes are applied. When you apply brakes, you don't hopefully press accelerator at the same time as well, right? When you're applying brakes, you don't have your foot on the accelerator. So there's no driving force. There's only a resistance force, a braking force. And they're saying the braking force acts on the car. Do we know what that force is? No. So there's a force acting on the car. That's the braking force. That's going to act in this direction. Let's call this force B. That's the braking force. Okay. There are resistances on both the objects. On trailer, there's a resistance of 200 Newton. On the car, there's a resistance of 600 Newton. These are the forces acting in the backward direction as well. What else? There's going to be tension. On the car, tension is going to act away from the car, right? That's what we assume, even though it's a tow bar, so it can end up being negative eventually. It can be in the other direction, but we start by assuming it like this, all right? That tension on the car acts towards the left side. Let's say this is T. On the trailer, we assume that the tension acts away from the trailer, right? We do it like we normally do it, right? Away from the object, in this case, tension acts in this direction. Are there any other forces acting? These are all the forces, right? The other forces are vertical. We've got weight of the trailer, reaction, weight of the car, reaction, but they're not relevant here because it's horizontal surface. There's no friction that we have to consider. We already have the resistances given, right? And it's a horizontal surface, so vertical forces do not really contribute to the motion. So that's not relevant here. All we have to do now is apply Newton's second law of motion. We have to find the magnitude of the force in the tow bar. That means tension. That's what we're looking for. Now we have less variables in case of trailer. Let's apply Newton's second law of motion on the trailer and see what we get from that. Resultant force equals mass into acceleration on the trailer. What's the forward force? Forward force is tension for the trailer. Backward force is 200. Mass is mass of the trailer. Where was that? 700. Into acceleration, acceleration is minus 12. Remember, it's a deceleration of 12. That means acceleration value is minus 12. What do we get from that? 700 into 12, which is negative, of course. And then 200 from there. This is giving me minus 8,200 Newton. Now, what does that mean? Minus 8,200 Newton, how is that possible? How can tension be negative? Remember, that's what we have discussed in a couple of other sessions as well, that tension can sometimes end up being negative. When you have a rigid object that's connecting two objects, in this case, it's a tow bar. This object that's connecting the car and the trailer, that's a tow bar. It's a rigid thing. If you have a string, so let's say you have a block and you have a string tied to it. A string can only pull objects. The string can only pull the object towards itself, right? String can only pull the object towards itself like this. However, if you had something rigid, for example, if you have a rod and that rod is connected to an object, that rod can both pull that object and also push that object. With string, you can't push the object, but with rod, you can also push the object. Okay? With rod, you can also push the object. So that's also possible. So sometimes what can happen is, when you have a rigid object like a tow bar, instead of string, for instance, you will assume the tension directions as usual, like you're doing here. You will assume that the tension is acting in this direction on the trailer and this direction on the car. But your final result can end up being negative sometimes. What that means is the actual direction of tension here is actually on the left side on the trailer and the right side of the car. That's the actual direction. Because it's turning out to be negative, that means the actual direction is opposite of what you have taken. So the trailer is actually being pushed to the left and the car is being pushed to the right by the tow bar. That's why this value is turning out to be negative. It's called thrust as well. But that's not explicitly part of your syllabus, the concept of thrust. So all that you need to understand is that the tension value can sometimes end up being negative. You just don't have to worry about that. They asked you for the magnitude of the force in the tow bar. You would say the magnitude of the force in the tow bar, magnitude is supposed to be positive. That is 8,200 Newton, and that's your final answer here. You'll just write that as positive number because the magnitude of that force is positive. Okay. Now, how is it possible the tension acts, that the force acts in this direction on the trailer and this direction on the car? Think about this. The car is applying brakes on itself. Now, car is reducing its speed, but the brakes are only being applied on the car. So car is basically applying a force on the left side. The tow bar was also moving. There are no brakes applied on the tow bar. So tow bar is kind of trying to move faster than the car now. So it basically pushes the car because of that. So that's why the tension acts in this direction. And similarly on the trailer as well, it's going to push it in the backward direction. But again, that's the logic of it. All you have to do is just remember, if you have a rigid object like this instead of a string, if you have a rigid object like this instead of a string, tension can end up being negative. Don't worry about that. It's not incorrect. It's all right. It is possible. Since they asked you for magnitude in this first part, you would write down the final answer as 8,200, and that's it. That's your final answer. Okay, I hope that makes sense. Now it says find the braking force in the second part. Now, where is the braking force acting on the car? Now we apply Newton's second law of motion on the car. Let's do that. Resultant force equals mass into acceleration. What are the forces acting on the car? Is there any forward force? There is no forward force. We can say that's 0. Backward forces B, T, and 600. These were the directions that you took. You leave them as they were, right? That equals mass, which is mass of the car, 1,600. 1,600 into acceleration, that was -12. Now we already have the value of t. Let's input that here, but remember that value of t turned out to be negative. You will put that as it is, minus 8200 here. Okay, minus 600 equals minus 19200. And that is going to give you the value of this braking force as well. Minus b plus 8200 minus 600 equals minus 19200. And that's going to give us the value of b. Let's see what this turns out to be. 8200 minus 600 plus 19200. And that's giving me 26,800. That's the braking force acting on the car. That's what we were looking for. We won't consider the failure forces. Well, we are applying Newton's second law of motion on the car. We can apply this formula on the object separately, right? So in the first part, we applied it on the trailer. In the second part, we're applying it on the car. We often apply on both particles in the same part and then solve them simultaneously. In this case, since the trailer equation only had one unknown, we could find that directly. And then for the second part, we use that value of t that we found in the second equation to find the value of b as well. So we are applying Newton's second law of motion on both the particles separately, like we often do on pulley questions, right? So it's very similar to that.